Okay, good morning. So today we are going to continue last time and start to talk about thin airfoil theory. So last time we ended in trying to compute the circulation of these four vortices so that the flow is tangential to the surface, right? So basically, in this case, it gives us one equation to solve for the circulation of the vortex, and from the circulation of the vortex, we then can compute the flow field. And in reality, a real flow field is actually going to be described not by just the four vortices, but by many, many more. And in the case of a cylinder, there is actually an analytical solution using a lot of calculus that tells you exactly what is the distribution of vorticity, what is the distribution of circulation on the entire surface. So there is circulation basically on the entire. You can think about the cylindrical sheet that encloses the cylinder, and the circulation is actually different everywhere. The density of circulation, that is, how much circulation do I have on a small section, right, is actually different everywhere. And in this particular case, actually this is a pretty representative case, that the circulation, which is the circulation over distance, right? Distance is basically, this is d, and this is the circulation around this distance, is proportional to, if this is a theta, is proportional to sine of theta. So which means the circulation is zero upstream and downstream. That's the same as what we did on Monday, right? On Monday we said because of symmetry, the vortex here and vortex here had zero circulation, and we only considered these four vortices. Remember? Okay, so the circulation here is going to be zero, and it actually achieves maximum at 90 degrees. So on the top of the cylinder there is most circulation, and then it goes back to zero at the downstream location. That's also consistent with what we did on Monday. And then the circulation becomes negative, which means the vortices on the lower part of the cylinder rotates in the opposite way, right? Counterclockwise instead of clockwise on the upper side of the cylinder. And it achieves the same maximum at the lowest point, and then goes back to zero. So this is the distribution of circulation. It's not just the single vortex, it's a continuum of vortex, a vortex sheet, just like the case we did back last Friday, right? Last Friday, we were looking at the wake of a cylinder, right? Basically a wake of a black body. So in the wake of black body, it was the another case where we have planar vortex sheet. A planar vortex sheet has a gamma over d that's constant, right? So a constant vortex sheet would represent a flat shape, while a vortex sheet of strength that is low, high, and then back lower represent a convex shape. And today we're going to look at even more complex cases of airfoils of actually arbitrary shape, and look at how can we go from the shape of the airfoil to the distribution of vorticity. And then from the distribution of vorticity, we can know the velocity, right? Actually, in this case, the velocity, in the case of a solid body, actually it is very clear, because inside of the solid body the velocity is zero, right? Just outside of the body the velocity is basically zero plus actually exactly this gamma over d. Okay, if you integrate over this rectangular shape, you're going to find out if the velocity in this leg is zero and these two legs have directions orthogonal to the velocity, then the velocity here actually has to be gamma over d, right? gamma over d actually has the unit of velocity. So that also means if you look at the velocity just outside of the cylinder, it's going to be 0 here, and maximum here, and maximum here, right? Okay, so we're going to use the same principle on the airfoils. Once we relate the shape to the circulation, we're going to then relate circulation to the speed just outside of the airfoil. And then from the speed just outside of the airfoil, we use Bernoulli's to get the pressure just outside of the airfoil. And then from pressure, what we can do? We can integrate the pressure to get what? Force, right? And then we can integrate the pressure times its lag to get what? Moment, right? Okay, so from there, we basically can relate the shape of the airfoil all the way to the aerodynamic performance, which is lift and moment. Okay, so first of all, I think I promised to actually derive Bernoulli's principle, right? And I'll provide a very simple derivation here. So from Navier-Stokes equation, we have du dt, that's acceleration, right, of a flow particle, equal to 1 over rho, so this is analogous to 1 over mass, times minus grad p, right? This is analogous to force. I mean, the difference is that instead of mass, we have mass per volume. Instead of force, we have force per volume, right? So the volume cancel out, and it's the same as F equal to ma. All right. So from this equation, and if we look at the steady state flow, so let's just imagine we have exactly on our previous case. This is a steady state flow, meaning if I fix my eye at one particular point and don't allow it to go with the streamline, the velocity over there is going to be constant. So here there is a significant difference between if you follow the streamline, then at t equal to 0, you're going to be looking at over here, but at t equal to, let's say, dt, you're going to be looking at over here, right? So that's, if you follow the streamline, then the flow particle is actually going to be changing in speed. But if you fix your eye either at the first point or the second point, then the speed is going to be constant. The pressure is also going to be constant. Okay, so let's actually look at this small segment. So we know the velocity here is u, right? Which means over a small distance, the flow particle has traveled a length of vector u times dt, right? Okay, so let me just denote this small length as L equal to u times dt. Then something we can manipulate on this equation is I want to multiply, I want to change this vector equation into a scalar equation by dot product both sides by this small l. Okay, on the left hand side, I want to dot it with the right hand side. So u dt, this is a vector dot with du dt, right? And that's equal to the right hand side, minus 1 over rho, grad p dot with dl, right? This is a vector, and the grad p, the pressure gradient, is of course also a vector, right? Okay, so let's look at what the left hand side gets us. The dt cancels, right? I mean, if we look at this du dt to be also the change of velocity along that flow particle over time difference of dt, then the dt cancels, and what we get is, what is u dot with du? Anybody knows what this can simplify to? Yes? D what? D. No, du means the changing velocity.
1/2 u squared.
Yes, it's the delta of 1/2 u squared. Okay, or 1/2 of, let me make it easier to understand. So instead of a magnitude squared, I want to write the magnitude square as u dot u. So a calculus basically can tell you that, okay, so if I have the dot product of two things, right? So basically the a small change in the dot product of let's say two vectors, x dot y is equal to x dot with a small change in y plus y dot with a small change in x. And here is just a special case where x and y are both u, right? So both of these are the same, which means they add up to 2 times u dot du, which also means if you have just one of u times du, it comes back to half of du squared. All right. So this is the same as this. So that's the left hand side. And the right hand side, what is grad p dot with dl? It's just the difference in pressure, right, between these 2 points. Okay, so it's basically 1 over rho times the d of pressure over this small segment. So let me write it more clearly. So if I denote this location as location, it's too thick. If I denote the first location at t equals 0 as location 0, the location at t equal to dt as location 1, then this is minus 1 over rho times p at 1 minus p at 0, right? Because the L points from 0 to 1. And the left hand side is half of u at 1 dot u at 1 minus half of u at 0 dot u at 0, right? Because on the left hand side, it means the velocity after the delta t minus the velocity before delta t, right? And on the right hand side, it means the pressure at the location 1 minus the pressure at location 0, right? They actually mean 2 different things, and they can only be related. I can only exchange the spatial difference with time difference if I know the flow field is steady state. All right, then I know, like, basically after the short amount of time, the flow particle has got into here. But then the speed after this short amount of time is exactly the same as if I didn't, instead of passing the time, I just freeze time but shift my spatial location, I would get the same velocity difference, right? So that's based on the steady state assumption. Okay, so basically here we know that Bernoulli's only holds for steady state flows, and with the steady state flows, we can just manipulate the blue equation into half of rho u1 magnitude squared plus p1, right, is going to be equal to half of rho u0 squared plus p0, which is basically what Bernoulli's is. Okay, so why is it useful? It is useful because if we can compute the velocity distribution just outside of the cylinder or an airfoil or any shape, right? We know the pressure distribution. Actually, the faster the velocity is, the lower the pressure is. And we just said along the cylinder, for example, the flow is 0 velocity here and the maximum velocity here, which means the pressure is going to be smallest or highest here? Highest over here, right? Look at this, right? Velocity plus pressure, velocity squared plus pressure is constant. Okay, of course, times half rho. So velocity being minimum here equal to 0 means pressure being highest over here. Velocity being highest over here means pressure being lowest over here. It's going to be the same for airfoils. Whenever we have high velocity, we have low pressure. Whenever we have slow velocity, we have high pressure. Okay? All right? So today we're going to use this to answer questions like this. So I'm putting this here just because it's a last year's quiz question. So maybe that'll bring your attention, right? So for example, by the end of the next lecture, we should be able to answer all of these questions. So I'm just giving, in the exam, right, I just gave out a plot actually from Xfoil, and which is the software we're going to learn this afternoon. And by the way, if you have time, install the software. I think our TA is going to send an announcement before you come to the lecture. You have two choices, either X-foil, which is kind of the old-fashioned drillers code, or M-foil, which is a newer but like requires MATLAB. Okay, I also cut off the result, like what is the angle of attack, what is lift coefficient, moment coefficient, etc. So I cut all of these out. And I just showed you the pressure distribution on top of on the surface of the airfoil. And if you haven't looked at pressure distribution on airfoils before, there is a very peculiar thing, is that we plot this axis backwards. Okay, and there is a kind of a semi-legitimate reason for that, but like I'm gonna show you later. So basically, maximum is here, minimum is here, right? Whenever you see something high, it means low pressure, but it also means high velocity, right? See Bernoulli's. So anything above is actually high velocity on the surface, which also means low pressure. Anything here means low velocity, which also means high pressure. And what does CP mean? So CP is pressure coefficient. The definition is pressure minus P infinity divided by half rho U squared. But like the easier way to remember this is, it is non-dimensionalized in a way that at free stream, this is 0. At stagnation point, which means when the velocity slows down to 0, it is 1. Okay, that's how I think I remember it, and I think is the easiest way to remember like how the CP, pressure coefficient, is non-dimensionalized. Is to relate this to velocity, right, using Bernoulli's. Okay, so lowest velocity, 0, right, CP equal to 1. And the free stream is going to be 0. Anything above is higher velocity than free stream. All right? Okay, so now the question is based on this graph. First is, okay, estimate the lift coefficient. What is the number on this CL, right? So, any idea in what do we use to answer the first question? The area in between these two curves, and why? Exactly. Lift is because of the difference of pressure on the upper surface and lower surface, right? So actually, whenever you look at an airfoil, I think I told you in the quiz that 1 degree angle of attack. So, and if you look at the shape of the airfoil, it's we're gonna look at thin airfoil theory later. It's pretty clear that this airfoil would generate actually even positive lift at 0 angle of attack. So when you are putting the airfoil at 1 degree angle of attack, it is going to be generating positive lift, which means this is going to be the upper surface, right? Lower pressure, higher velocity. This is going to be the lower surface, higher pressure, lower velocity. And when you look at the difference between upper surface and lower surface, this magnitude, right, is the pressure difference. And if you integrate this, which is really looking at the area underneath, not underneath, but in between, right? The integral on the upper surface minus the integral on the other way. The integral on the lower surface minus the integral on the upper surface. But this is reversed, right? So the area in between is going to be the lift. That's right. Okay. And then the two other questions, I think you have to understand thin airfoil theory to answer is, at 0 degree angle of attack, what would be the lift coefficient, right? Previously, I told you the thin airfoil theory predicts that dCl d alpha equal to 2 pi, right? And this is also a result you are going to get if you do this week's homework, okay? And you're actually going to get the same answer for both of the two questions, right? No matter how you model it, you're going to get 2 pi. And the thin airfoil theory is also going to get you 2 pi. So if you figure out question 1, you can figure out question 2 just by, okay, multiplying 2 pi by the, not by 1, but you have to convert 1 degree to radians and then multiply by 2 pi. Like, this is This is actually a uncommon mistake because the answer you get would be ridiculous if you actually just directly multiply 2 pi by degrees. Okay, you're gonna get like huge lift coefficients and things like that. So most of the people remember to convert the degree into radians before multiplying by 2 pi. At 1 degree angle of attack, the third question, the airfoil has a ratio of moment coefficient over lift coefficient, okay, of minus 0.07. Where is the center of lift of the airfoil? Not at 1 degree, but at 0 degree angle of attack. Okay, so this is, I think I'll hold off the answer to this question before we actually explain thin airfoil theory. All right, okay, so let's actually dive into this. So first of all, the thin airfoil theory is actually based on the vortex-centric view of an airfoil. So this is, if you haven't looked at homework yet, basically this is our homework, problem 1 and problem 2. And I won't solve it for you, but like it is really based on using either one vortex or 2 vortices to describe the flow on airfoils, right? Here, we use the 1 control point if we have 1 airfoil, and the 2 control points if you have if we have 1 vortex, 2 control points if you have 2 vortices. And thin airfoil theory is based on not 1 vortex or 2 vortex. It's again based on the continuous vortex sheet along the whole chordwise direction of the airfoil, right? The vortices would point all towards the board in the span along the spanwise direction, but there is a whole sheet of such vortices along the chordwise direction. And the circulation of these vortices are not calculated by enforcing no flow condition along just the 2 control points, but it's enforced everywhere along the entire length of the airfoil. So think about this: when you're doing homework, you're going to get 1 equation for this. You're going to get 2 equations with 2 unknowns for this. With thin airfoil theory, you get an unknown function, okay, and you have to enforce, and you have to solve for this unknown function by enforcing an equation that has to be true for any eta, right? For any eta going from 0 to 1. So here, of course, I want to go through the derivation of thin airfoil theory. You can like look it up in any standard textbook. I usually find like even if you ask a random PhD student in this department, I would say like less than half of them can actually derive this without looking up the internet or something like this. So I won't go through this. Like it'll take the entire class, and I'm not sure if it's worth it because you're going to forget it right afterwards. So what I'm going to be doing is really just explaining what the assumptions are, and then like straight jump to the result. Okay. So the assumptions of thin airfoil theory is the following: the flow around the wing is sum of the free stream. Well, that's the same for the lifting line theory and everything else. Induce the flow of a collection of spanwise bound vortex sheet. So this is very similar to the lifting line theory, except for in the lifting line theory, there is only 1 bound vortex, right, through the quarter chord. Now we have infinitely many vortices distributed from the leading edge to the trailing edge, but running exactly in the same direction as the bound vortex in lifting line theory. Okay, and thin airfoil theory also assumes all the vortices are approximately on the xy plane. So if you have an airfoil that goes like this, like in a Formula 1 car, for example, have you looked at what airfoils they get? Thin airfoil theory is not going to be very good. Okay, so the camber line of the airfoil needs to be pretty small. Okay, and the induced flow has to be much weaker than the free stream, because we're going to be making, in the derivation of thin airfoil theory, they make approximations, exactly the kind of approximations I ask you to make in the homework questions. Okay, I think I asked to like ignore, for example, the the horizontal, the x component of the induced velocity, exactly because it's much weaker than the free stream, right? And I also asked you to approximate like angles, like alpha can be used to approximate sine alpha or tangent alpha, things like that. These are all used throughout thin airfoil theory. So basically, all of this assumes that the induced flow has to be much weaker than free stream. Okay, and so this is how useful the thin airfoil theory is. It basically is the most, I would say, the most useful non-computational tool. So if you want to kind of intuit how the shape of an airfoil would change, how if you change the shape of the airfoil would change the aerodynamic lift and moment without using a computer program, this is the best tool we have, right? Anything else, anything more accurate, you need to use a computer program like the one we are going to introduce this afternoon. So how it does is that it basically enforces zero normal velocity, just like in your homework, but around the whole chord of the airfoil. And that gives you a relationship between the shape, which determines, right, what is the angle of the wall normal, right, and the vorticity or the circulation, right. Once you determine the circulation, you basically get velocity, right, because the velocity is induced from all the circulation plus free stream. Now, once you have the velocity, you use Bernoulli to get the pressure, right? You have the pressure on top and on bottom, and then the pressure integrates to lift and moment. So by these really 3 steps, you go from the shape or any change in the shape, right, to a change in the lift and moment. So that's how thin airfoil theory works. Now, before going into thin airfoil theory, let me just tell you in what ways it's wrong. Okay, so first of all, the vortices can be far from the XY plane if your airfoil is not really exactly flat. And the induced flow is not going to be exactly tiny compared to free stream, and especially in 3 scenarios. One is if your airfoil is thick, right? You have to actually have stronger induced flow for the flow to actually go around the thick airfoil, just like in our cylinder case, right? If you remember, like what we derived on Monday, the circulations and the induced flow from the circulations of a cylinder is not small compared to free stream, right? It has to be comparable to free stream to actually cancel the direction of the free stream normal into the surface. Okay, and at high angles of attack, even if you have a thin airfoil, the induced flow is going to be getting stronger and stronger. Okay, and that is because the angle of attack, at high angle of attack, the flow actually, the free stream actually wants to go into the bottom of the airfoil and out of the top, right? So you need a stronger vortices to actually cancel these normal components to have the flow go tangential to the surface. And okay, around leading edges, even if you have a thin airfoil, small camber, and small angle of attack, you are still going to be wrong. Like basically, if you look at thin airfoil theory result, it's never going to be correct exactly at the leading edge. Okay, just because on the leading edge, the flow goes, the free stream goes right into the geometry, right? And over near the leading edge, you need the strong vortices to actually cancel that free stream component that goes right normal into the surface. So the assumption that the induced flow is small compared to free stream is actually never correct at exactly at the leading edge. It's just if you have a very thin airfoil, it's only incorrect in a small region in the leading edge. If you have a thick airfoil, then it's incorrect over a bigger region near the leading edge. The third aspect it is wrong is that, of course, starting from the beginning to now, we never considered any viscous effects, right? The portion of Navier-Stokes equation we have written down only has the pressure as a force. It doesn't have the viscous, which is another force. Which means the thin airfoil theory, if you if you strictly believe in it, predicts zero viscous drag for everything, which is fantastic but not true. No stall whatsoever, right? You can generate extremely high lift coefficients and still no zero viscous drag, which is fantastic but not true. And it has no explanation of the Carter condition, so I haven't told you about the Carter condition yet, but even in your homework, there is an implicit reflection of the Carter condition in that all your control points are downstream of the vortices. So that, right, do you feel like that's kind of peculiar, right? That actually is an inherent bias in one side versus the other side. So basically, it says that it's more important to enforce the downstream velocities to be having zero rather than the upstream velocities to be zero. So that is actually an implicit consequence of the Carter condition, which basically says that, okay, over the trailing edge, you are not allowed to have very fast flow around the trailing edge. But on the leading edge, it's okay to have very fast flow around the leading edge. That cannot be explained until we explain the viscous effect, right? Which is really, there is a boundary layer. The boundary layer is very thin in the leading edge. It becomes thicker and thicker on the trailing edge. If you have faster flow around the trailing edge, the boundary layer is going to separate. But if you have very fast flow around the leading edge, it's much less likely to separate because the boundary layer is very new and very fresh and is much harder to separate on the leading edge. Yes?
Is there a general rule of thumb of when, like, a thickness to chord ratio of when thin airfoil theory stops being accurate?
Good question. There is no kind of a strict rule, and it actually depends on what you want to use for it, right? So as I said, on the leading edges, even extremely thin airfoils, you're going to be wrong if you look at, for example, the pressure distribution and velocity distribution over there. But if you look at the overall like lift and the moment, it can be pretty accurate even if you are like all the way to like 20% thickness. So yeah, and also it depends on exactly the shape, right? So if you have shape that's actually more, if you have a very streamlined shape, it tends to be more accurate. And if you have more weird shapes that actually would force the flow to go not in the streamwise direction, then it would be wrong earlier than otherwise. Okay, so what are the results of the thin airfoil theory? So let's actually skip all the derivation and show just the result. Don't know, sometimes it doesn't work. Let me just click. Okay, this works. Oh, I don't know. Okay, so you see a lot of complicated mathematical expressions over here. Basically, that's a direct copy from the long derivation that comes out of the thin airfoil theory. Okay, but what is critical here is that we have the lift coefficient integrated over here. We have the moment coefficient integrated over here. And by the way, the moment coefficient is defined as the aerodynamic moment around the quarter chord. Okay, so that's why if you look at the formula, there is a 1/4 minus x over here, right? And g is gamma. That's circulation. That's it's actually not gamma. It's gamma over d, right? It's the circulation per length over the airfoil. So right now I have 0 angle of attack and 0 camber, so it's exactly a flat plate. That's why like I have my vorticity distribution, my gamma to be exactly 0. And yeah, so XCP is like the center of lift. So if the moment is going to be 0, the center of lift is exactly at the quarter chord. Okay, so the bigger, if I have positive, okay, so from this equation, you can probably already understand what is the definition of the moment. So positive CM, is it nose up or nose down? Can you just look at the center of lift and tell me maybe from this equation, can you guess or deduce if moment coefficient positive means nose up or nose down? A hint is think of, just use an example, right? In what case would XCP be 0? In what case would the center of lift be exactly at the leading edge? X equal to 0 is the leading edge. Well, for XCP to be equal to 0, Cm has to be equal to, for example, Cm is equal to 1/4, Cl is equal to 1, right? That's a case where the lift is going to be exactly at the leading edge. So a positive moment means the lift would shift from the quarter chord all the way towards the leading edge, right? That means it's what kind of moment? Oh, so if the center of gravity is at quarter chord, for example, okay, and your Cm is going to be 1/4 and Cl is going to be 1, such that your center of lift is at the leading edge, in what way would the airplane rotate? Would go nose up, right? So a positive Cm means a nose up moment. Okay, a negative Cm means a nose down moment. Okay, so if Cm is minus 3/4 and Cl is equal to 1, then you're going to get XCP equal to the trailing edge, right? The airplane would go nose down. So that's basically tells you the sign of the Cm. Okay, so then let me tell you what these variables that I would be tuning means. I don't know why I have so many. Okay. So I have A0, A1, A2, A3, A4, A5. So in thin airfoil theory, there is actually infinitely many such A's. Okay, so it's something called like a cosine series. You have basically every A is multiplied by a different cosine function with a higher and higher frequency to get you the shape of the slope. So Sx is the slope. If you look at the formula, it's basically a bunch of A's. If you look at the book, there are infinitely many terms after that. So S is the slope of the airfoil. So remember, like, we are enforcing no zero flow conditions everywhere on the airfoil. So this slope actually tells me is what I mean. So this slope calculates what should be the direction of the total flow, the free stream plus all the induced flow everywhere on the airfoil surface. If S is positive, it means the airfoil is sloping upwards. S is negative, which means the airfoil is sloping downwards. And if you integrate S over, well, it says Y, but like it's just a different variable, right? So if you integrate S, you would get what? Get the Camber line, right? For positive S, you go downstreaming X, the airfoil goes upward, right? For negative S, as you go towards positive X, the airfoil slopes downward. So let me just do a bunch of things to actually, let me just disable this vorticity distribution and just look at the shape, the Camber line. So if I change A0, look at A0. A0 is a constant, actually negative constant. So if you increase A0, right, the slope gets negative everywhere and the Camber line just goes straight down. Does it make sense? So this is actually an angle of attack term, right? I mean, the airfoil pitched up like this is exactly the same as if the free stream goes up and the airfoil didn't change, right? So basically A0, a constant term in the slope, basically represents angle of attack. And let's now look at the vorticity distribution to see G. Okay, so this vorticity distribution is basically the crux of the derivation. I mean, like the end of the derivation for thin airfoil theory is that you get this formula. Okay, and A0 is going to be multiplied by this guy. Remember, like we are setting all of the other A's to be 0, right? Only A0 is non-zero, and we get this distribution. Yes, question?
Can you explain what A is again?
A is a bunch of things. A is the coefficients for the cosine series expansion representation of the slope of the airfoil. So here I'm exactly trying to explain what each of these A means by changing them one by one. So we only have explained A0 up to now. So A0 controls a constant slope, right, which really represents the angle of attack of the airfoil. So if you change A, you would be pitching the whole airfoil up more or down more. A0. So I'll explain A1, A2, etc. later. All right. Okay, and so this is basically the result of changing the angle of attack. And what you see, the first thing I want to tell you that this is not correct is exactly at the leading edge. The vorticity distribution, the circulation per length, goes to infinity at the leading edge, which is of course not a physical result. What you're going to see in reality is that the thinner the airfoil is, the higher the peak goes, but never infinity. Okay, so if you have a thick airfoil, maybe it kind of comes down over here. If you have a thinner airfoil, it comes down over here. But like, so thin airfoil theory, if you just stick to the theory, it goes to infinity. But the most remarkable part about this function is that, you see, this is the vorticity distribution, right? Vorticity actually along the airfoil tells you the difference in the velocity on the upper surface and on the lower surface, right? So over here you have a small difference in velocity up and lower. Here you have bigger difference up and lower. And we have just said that the difference in velocity represents a difference in pressure, right? And I'm going to derive this more carefully in the next lecture, but if we do assume that the induced flow is small compared to the free stream, then there is an approximation that says that the difference in pressure is actually proportional to this vorticity. So you have small difference in pressure up and lower surface over here, big difference up and lower here. And if you want to integrate this whole thing under this purple curve, that's how you get the result 2 pi. Okay, pitching this camber line by epsilon. So essentially changing A0 by epsilon gives you a purple curve whose area underneath is 2 pi epsilon. All right, that can be, I mean, if you are interested in doing complex calculus, you can integrate that function and see yourself. All right, so this is A0, the angle of attack, and this is the pressure difference it gives you. The curve underneath integrates to 2 pi, and also if you get a flat plate and load the weights on the flat plate according to this distribution, guess where the center of the weight is? Which side is it? Which side has more weight? If you load the weights on the flat plate according to this, the left side, right? By how much? Well, you need math to do that, and if you do the math, you'll find out is exactly 1/4. Okay, so this is actually this function here, and the fact that this function has a center of weight equal to 1/4 is actually the reason the quarter chord is so important in aerodynamics. Okay, and like you asked, for example, how accurate a thin airfoil theory is, right? And the fact that if you increase the angle of attack, the increment in lift is concentrated at the center, at the aerodynamic center, at the quarter chord. Is pretty accurate all the way. It's very accurate if you have a 10%, 12%, 15%. It starts to be less accurate when you have 20% and more. So this is actually one of the most remarkable thing about the thin airfoil theory is actually this function and the fact that the area underneath is 2 pi, the center is quarter chord. Okay, any other questions about the A0 term? I think I may have time to say something about the A1 term before the end of the class. But I want to. But A0 term is actually the most important. All right. Any questions? Okay. So let's actually remove the A0 term because it just represents the angle of attack, right? I mean, just you are pitching the whole thing up and down. So let's set it to 0 and only change the A1 term. And again, let's look at the shape first before we look at the resulting vorticity. So we are just looking at the Camber line, right? Okay. A1 is here. Where do I get this? Actually, where do I get this? Yeah. So A1 is this guy, and if you make it positive, it goes like this. If you make it negative, it goes like that. Okay, so t of x is actually a arc cosine function, and basically you're taking a cosine function and on the arc cosine function, and what you get, but there is a 2x here. So again, like if you use the trigonometry identities, you're going to see that the A1 term is going to be multiplied by a parabola. Okay, so this guy is exactly a parabola. So the s for this guy is a linear function. So if you plug in this cosine into the cosine, right? Of course you get a linear function. But remember the Camber z is the integral of that linear function s. So you get a parabola over here, and so this is basically the second question in your homework, right? Like a parabolic Camber. And let's start to look at what is the resulting circulation. It's going to be, remember, t is like an arc cosine. It's sine of an arc cosine. What is it? Pi, sorry. Just look at the shape. What does it look like? It's a semicircle, right? Like a sine of an arc cosine is basically square root of 1 over x squared, right? Then normalized by this guy. So the vorticity distribution and the associated pressure distribution is a semicircle. And the most important thing about this is that it is symmetric, left and right, which means the center of pressure, the center of lift is where? Half chord, right? If you get a parabolic, camber, and if you pitch it at the 0 angle of attack, what you're going to get is a center of lift that's half chord, not quarter chord. What is the sign of the resulting moment coefficient? Again, look at this. Well, xcp is equal to half, right? So that's the center of lift is half chord. But what is the sign of cm? It's negative, right? So basically, yeah. So you expect that actually we're going to see most airfoils with camber, unless you specifically design it with a big A3 term, which we're going to explain on Monday, is going to have negative moment coefficient. Okay, So let's actually get back this afternoon and we look at what if we use something more complex than thin airfoil theory to look at aerodynamic performance of airfoils. All right.